This is the first section of chapter 4, Flows in Networks 2, and this section is on lower capacities. So in this section we introduce a lower capacity on an arc, and it will be shown like this: two numbers in brackets, where the first number represents the lower or minimum capacity of the arc. In this example here it's 7, and the 15 represents an upper or maximum capacity of an arc. So we're used to seeing this already, just a single number representing the upper capacity, but this is new. So we must have this minimum capacity flowing through this arc for this to work. You can't have anything lower than this minimum capacity flowing through this arc. Now in this diagram here, where I've got two arcs and I've got these nodes here, A, B and C, and I've got the maximum and minimum capacity of arc AB and maximum minimum capacity of arc BC. If B were to equal C, so if this value here was to equal this value over here, C, so B was equal to C, then arc AB is saturated, it's at its maximum capacity, and arc BC, this arc here, is at its minimum capacity. In other words, this arc, the flow here needs to be at its maximum just to supply the next arc next to it, adjacent arc, with its minimum capacity. This has to be at full flow here to enable this to flow at its minimum capacity. If, however, we have this first arc here at its minimum, and that matches the maximum capacity of the second arc, I'm not sure why I put capacity there, that should say saturated. So in other words, is if A, the minimum capacity of arc AB, is equal to D, the maximum capacity of arc BC, then arc AB is at its minimum, so this is at its minimum here, capacity, and arc BC is saturated. In other words, this has to be at its minimum because this minimum is equal to the second arc saturated, so this can't go any higher than its minimum here, otherwise we'll be going over the saturation point of this arc, which is not allowed. So we'll just highlight that here so you can see what matches up with what in the diagrams. And lastly, if we're required to work out the value of a cut, well, this is equal to the maximum capacities which flow from the source to the sink from S to T, going across the cut, minus the minimum capacities of any arcs which are flowing from T to S, from the sink to the source. Example 1. In the diagram, arcs AB, BC and BD represent part of a directed capacitated network. The diagram is shown here. Deduce the value of the flow in each arc. So we have the maximum and minimum values of the flows in each of the arc. Let's start by looking at the minimum flows that flow out of the arc, and I have 3 as a minimum there and 2 as a minimum there, so I cannot go below a flow of 3 in arc BC or below a flow of 2 in arc BD. So I need to have flowing into this vertex here, this node here, at least 5. And if I have a look, that is the maximum of the flow along arc AB. It can't go any higher than 5. So this has to be its maximum to allow flow of a minimum along these arcs. Okay, there aren't any other combinations, so I can't go any higher than the minimums because the maximum that can flow in is 3, and I can't go below this. Is 5. I can't go below this 5 because 3 would not supply enough for these to be at their minimums. So I'll write something like this. So I've got here, since the flow into B needs to be at least 5, AB has a flow of 5, so this is saturated, so I'll just put 5 here to show the flow along that arc. BC has a flow of 3, okay, that's at its minimum capacity, and arc BD has a flow of 2, that's also at its minimum capacity. Now remember, we're using the conservation condition, which means that the flow into a vertex equals the flow out of a vertex, so we've got 5 going into B and then 5 coming out of B. Example 2. The diagram shows a directed capacitated network. The numbers on each arc represent the lower and upper capacities of that arc. Part A. By considering vertex C, calculate the flow in these different arcs here. Okay, so what I've done, I've just taken that part of the diagram and drawn it here, so I can see that there's 2 arcs flowing into C, one from vertex B, one from S, and then there's one flow out to vertex G, and I've put on here the maximum and minimum capacities of those arcs. Okay, so we need to consider the maximum and minimum capacities. So if I look at the, let's say the arcs going into it, I can see I've got a minimum capacity of 4 here and a minimum capacity or flow of 2. So from these 2 arcs, BC and SC, I've got a total minimum capacity of 6 flowing into C. So I must have at least 6. I can have more than 6 and actually have up to 14. So between 6 and 14 going in. So I guess if I were to replace those with a single bracket, I could put this down. Okay, that's basically the 2 arcs combined. So sorry, not 4, 6. So a minimum of 6 going in. Let's get my numbers right. And 6 plus 8, that should be 14. So yeah, if I replace them with single numbers, 6 going in, 14 coming out. So I've got to have a minimum of 6 flowing into C. Now, if I have a look, that matches the minimum of, or the maximum of 6 flowing out of C. So these arcs here, BC and SC, are going to be at their minimum, and arc CG is going to be saturated. So that now tells us what our answers are going to be. So part 1, the flow in arc SC, that's going to be at its minimum, so that's 2. Then the second one is the flow through arc BC, so we've said that's also going to be its minimum. And then lastly, the flow through arc CG, and we said this one's at its maximum of 6. So we have 2 and 4 make 6, and we have to have 6 flowing out. Part B, explain why arcs DE, AE and BE must all be at their lower capacities. So I've highlighted those arcs on the diagram here. We need to look at the maximum and minimum flows. So there can only be a maximum flow of 11 out of vertex E. Now let's have a look at the flows flowing into E. It's got 8, 6, 5, well that's well over 11. Let's look at their minimum capacities. So 4 plus 4, that's 8 plus 3 is 11, right? So these need to be at their minimum capacities because that matches the maximum capacity out of vertex E. So the arcs need to be at their minimum capacities to match the maximum capacity out of vertex E. So that 4 plus 4 plus 3 has to equal 11. In part C, calculate the flow in GT. So I've added onto the diagram all of the flows that we've calculated so far, and we want to work out the flow that's in this arc. It needs to be a minimum of 8 and a maximum of 11. So we have this arc flowing into it, CG, and that's got a flow of 6, that's at its maximum. And then this arc BG, well, that needs to be a minimum of 5. So we need to have at least 5. Now 6 plus 5 makes 11. That matches the maximum of this one. So arc BG cannot go any higher than 5. It has to be 5 because the conservation condition says that the amount of flow into a vertex needs to match the flow coming out of the vertex. So that has to be 5. So we've calculated the flow in GT, and that has to be 11. I've just added a reason why, since CG equals 6, okay, already calculated, and BG must be 5 to get the 6 plus 5 going in, has to equal 11, can't go over 11. That's why this one has to be 5. Example 3. The diagram shows a feasible flow for the network given in example 2. So the example that we've previously worked out. What we need to do in part A is use flow augmentation to find a maximum flow through the network. Right, so we start with a labeling procedure, which basically is going to show by how much I can increase the flow through each arc and how much I can decrease the flow through each arc. Now the only way that this differs from the previous chapter flows in networks 1 is that previously we could reduce the flow down to 0 in that section. Here we can only reduce the flow down to the minimum capacity. So apart from that small difference, the labeling procedure is the same. So I'll do a couple of these as examples and then I'll just complete the rest because it will take too long to go through every single arc. So if I were to start, let's say for example with arc SA, I have a look, it's currently got a flow of 17. I can increase it up to 20, so that can be increased by 3. And in the previous section we could say this could be decreased by 17 down to 0, but this can only be reduced down to 15, so it can be reduced to 2. Let's do another arc. Let's do this one here. So this currently has a flow of 7, so it cannot be increased anymore. It's at its maximum capacity, it's saturated, and it can be reduced down to 4, so that one can be reduced by 3. So I'll just put 3 in here. Let's have a look at this arc here. It currently has a flow of 2. It can be increased up to 8, so it can be increased by 6. It's currently at its minimum capacity, so it cannot be reduced anymore, so it's going to be 0, and I think I'll do one more before I just fill in the rest of the diagram. Let's say this one here, this currently has a flow of 8, it can be increased by another 4 up to 12. Its minimum flow is 6, so it can be reduced by 2. So this is my completed diagram. So I'm now ready to find a flow augmenting route. Now remember, that's a route which takes me from the source to the sink without using a route which has 0 from S to T. Now the easiest way to do that is to look at the vertex that go into the sink and then look at the ones where we have 0 going in. So ET, so I'll just put a cross through that. I can't use this one. So any route that's going to end here is no good, and this one also has 0 flowing into T as well. So any route that ends here we're not going to use. Actually what I might do is just highlight them like this. So we cannot use routes that end that way. So that means that actually I'm going to have to sort of maybe snake along here, go around the outside. Let's see if there are any other routes which have 0 going from the source to the sink. Yeah, there's this one here, CG. And I think the only other one I can find here is SB. It has 0 going from source to sink. So no point going anywhere down here. Let's have a look. Is it possible to go? No, I get that way. Might need to go backwards, and then in which case I'd be going 0 that way, so that's no good. So it looks like it's going to be S, A, D, F, T. Let's just double check, see if there aren't any other routes. So if I went along here, went backwards along there, oh, that would be 0. So that's no good. So there are some backward routes I possibly could use, but they've got 0, which I can't use. So my flow augmenting route is going to be S, A, D, F, T. So we'll just highlight that route on my diagram. So we're taking this route here, and I'll look for the smallest value on this route to see how much I can increase the flow by. So that's 2. So now let's relabel it, increasing the flow by 2. So if I can increase the flow by 2, that means that the 3 here means I can only increase by 1. That means that the flow back, that can now be increased by 4. So basically we're going to subtract 2 from these numbers going from S to T and increase the reverse flow by 2. So let's just do that. So decrease by 2, increase by 2, decrease by 2, increase by 2, decrease by 2, increase by 2. So our initial flow before augmentation was 17 plus 7 plus 2. So 17 plus 7 plus 2, those arcs flowing out of the source, and our improved, our maximum flow, we add 2 to that to get 28. And part B, show the maximum flow on a diagram, or on this diagram. Okay, so let's get rid of all the bits we don't need. So these are all the flows which we've remained unchanged. So I don't want to touch any of these. So we'll get rid of those. So all I need to do now is to change the flow along that highlighted arc and increase those flows by 2. Okay, so the 17 here increased by 2, so we're going to make that 19, like this. Then the next arc here increased that flow to 10. Next arc here increased that to 6, so 2 more. And then do the same here, increase that 4 to 6. So that completes part B. Now we're not asked to do it on this question, but I could prove that this is a maximum flow by finding the minimum cut. And actually, if I were to put a cut across here, then the flow across that cut is 11 plus 11, 22, plus 6, which is 28. So there we have a proof using the minimum cut maximum flow theorem that 20 is indeed the maximum flow, but it's not required in this part of the question. Example 4. Here is the network used in examples 2 and 3, and what we need to do in part A is find the capacity of the cuts C1, C2 and C3. So let's start with C1. So we want to see which way each of the arcs is flowing. So we have that flows in, this flows in, that one flows in, this one flows in. They all flow in. So when they flow in, we add together the maximum flow of each of those paths. So I'll just highlight those numbers. So that's going to be 12 plus 6 plus 8 plus 7 plus 8. It gives 41. So cut number 2. So we'll just get rid of these here, and we'll look at the direction things are flowing in that one. So that flows into the cut, that flows in, this flows in, this flows in, this one flows out, and this one flows in. So maybe the one that's flowing out I'll do in a different colour, maybe blue, so it's flowing out. Anything that flows in, we add the maximums, so 12, 6, 8, 7 and 6, and we subtract the minimum of anything flowing out, so that's going to be subtracting 4. So our calculation is going to be 12 plus 6 plus 8 plus 7 plus 6 minus 4, and that gives 35. And then cut 3. So same thing again, so we'll get rid of all of these here, and we're just going to concentrate on the direction of the flows. So DF flows into the cut, ET flows into the cut, and CG flows into the cut. So it's just adding the maximum of those flows, 6 plus 11 plus 11. So 6 plus 11 plus 11, which is 28. So explain what this shows about the maximum flow. So by the minimum cut maximum flow theorem, the maximum flow is 28, as shown as the previous example. So we found the minimum cut, and the flow through that cut is 28, and that's the same as the maximum flow. And you can see by the previous cuts that these are not minimum cuts here. So you should now be able to do exercise 4A, which you'll find on pages 117 to 119 of the textbook.